3.2 Concavity and the second derivative. Southwestern College, Professor Maria Olivas. Concavity and the second derivative. Objectives. Determine intervals on which a function is concave up, concave down. Find point of inflection. Use the second derivative test to find relative extrema. 1. Concavity. Definition of concave up, concave down. Here we have two coordinate planes. They are both focused in quadrant 1. In the first coordinate plane, we have something that looks like a parabola opening up. Above the parabola, it says the second derivative of f is greater than 0, or f double prime is greater than 0. In parentheses under that, it says concave up. On the parabola, it looks like there are tangent lines drawn. One has a slope equal to -2, one has a slope equal to -1, one has a slope of 0, one has a slope of 1, and the other has a slope of 2. Underneath the coordinate plane, it says f double prime is greater than 0, means that the slope is increasing, so f is concave up. I have drawn a cloud around the part that says f double prime is greater than 0, concave up, the part that is above the parabola. Above that, I wrote second derivative is positive. I've underlined the part that says slope is increasing, so f is concave up. If you look at the slopes as we go from left to right, the slopes are increasing. It goes from -2, and I'm going to circle these slopes. It goes from -2, -1, 0, 1, and 2. So as the slope is increasing from left to right, we can see that this function is concave up. On the right-hand side, we have another coordinate plane. We have a function that looks like a parabola that opens downward. Above the parabola, there appears to be tangent lines, and they go from left to right. The one starting farthest to the left says slope equal to 2. Then we have slope 1, then we have slope 0, slope -1, slope -2. Underneath the parabola, it says f double prime is less than 0, and in parentheses underneath that, it says concave down. Underneath the coordinate plane, it says f double prime is less than 0, means that the slope is decreasing, so f is concave down. And if you look at the slopes going from left to right, you do notice that they are decreasing. It goes from 2, 1, 0, -1, -2. Given f is continuous on the open interval from a to b, 1. If f double prime of x is greater than 0 for all x in the open interval from a to b, then f is concave up on the open interval from a to b. 2. If f double prime of x is less than 0 for all x in the open interval from a to b, then f is concave down on the open interval from a to b. A point of inflection is a point on the curve at which concavity changes. Also, 1. F is concave up when f prime of x is increasing. 2. F is concave down when f prime of x is decreasing. So I have drawn something that looks like a cubic. So it is an increasing cubic. Right in the middle of the cubic, I drew a point and I drew an arrow pointing at it, and I wrote point of inflection, and I've abbreviated that underneath there with POI for point of inflection. If you notice to the left of the cubic, this area is going to be concave down. So I'm going to write down the words concave down to the left of this point. To the right of the point, you're going to notice that the function is concave up. So I'm going to write down the words concave up to the right of my point of inflection. And then from the words point of inflection, I'm going to draw an arrow pointing to the right, and I'm going to write down that this point of inflection represents where concavity changes. Example 1. Consider the function f of x equals x raised to the third power minus 5x raised to the second power minus 8x plus 5. Find the intervals on which the function is concave up and concave down and the locations of any points of inflection. Step 1. Find f double prime of x, or find the second derivative of x. After we find f double prime of x, we're going to find where f double prime of x is equal to 0, or where f double prime of x does not exist. Because remember, when you are looking for possible points of inflection, you are going to want to find either where f double prime is equal to 0 or where f double prime does not exist. In this particular case, we have a polynomial function, and I know that when I find the first derivative and the second derivative of this polynomial function, I will still end up with a polynomial function. So that means it's going to be continuous everywhere. So we really don't have to worry about finding anywhere where this function or where the second derivative does not exist. But that is always a possibility, and I want to just write it down to remind you that you need to look for these two situations. Let's begin by finding the first derivative. So I'm going to find the first derivative of f of x, so that's going to be f prime of x is equal to 3x squared minus 10x minus 8. Then I'm going to find the second derivative. F double prime of x is going to be equal to 6x minus 10. I'm going to take the second derivative and set it equal to 0. So 6x minus 10 equals 0. I'm going to add 10 to both sides. The negative 10 and the positive 10 on the left-hand side are going to zero out, and we'll just be left with 6x equals 10. I'm going to divide both sides of my equation by 6. On the left-hand side, the 6's are going to divide out, and we'll just be left with x is equal to 10/6. But 10/6 will simplify to 5/3, so x is going to be equal to 5/3. I'm going to lasso in the part that says find f double prime of x equal to 0 or f double prime of x does not exist, and I'm going to shrink it, and I'm going to move it slightly to the left hand side to give me more space on the right hand side. I'm going to draw a vertical line segment going down to separate the work that I did here on the left hand side from the work that I'm going to do on the right hand side. On the right-hand side of my vertical line segment, I'm going to write down step 2. After that, I'm going to write number line test. I'm going to draw a one-dimensional number line. At the center of my number line, I'm going to label it with the value 5/3. I'm going to go ahead and choose some test points here. I'm going to write beneath the 5/3 that this is equal to 1 and 2/3 because that gives me a better idea of what test points I can choose. To the left of 5/3, I'm going to choose the test point of 0. To the right of 5/3, I'm going to choose the test point of 2. And I'm going to substitute into my second derivative these test points. F double prime of 0 is equal to 6 times 0 minus 10, which is equal to 0 minus 10, which is equal to negative 10. F double prime of 2 is equal to 6 times 2 minus 10, which is equal to 12 minus 10, which is equal to 2. I'm going to label my number line with f double prime so that I know this number line is associated with the second derivative. Above the open interval from negative infinity to 5/3, I'm going to write a negative symbol and circle it, and I'm going to write down the words concave down right underneath that negative symbol, but right above the number line. Above the interval from 5/3 to infinity, I'm going to write a positive sign, circle it, and underneath that I'm going to write concave up. I've highlighted the negative symbol, the positive symbol, and the 5/3 because there was a sign switch on both sides of this value of 5/3. That means that 5/3 is going to represent the x coordinate of our point of inflection. I've drawn a horizontal line segment to separate the work that I did from up above here from the work that I'm going to do down below. Step 3 is going to be my conclusion. I'm going to write down f is concave down on the open interval from negative infinity to 5/3, and f is concave up on the open interval from 5/3 to infinity. And I'm going to write down there is a point of inflection at x equal to 5/3, and the location of that point is going to be at 5/3, comma, question mark. I don't know what the y coordinate of my point of inflection is, so I'm going to find it. I drew an arrow pointing upwards, and I'm going to do the work right underneath where it says f double prime of 2. I'm going to write f of 5/3. f of 5/3 is equal to 5/3 raised to the third power minus 5 times 5/3 squared minus 8 times 5/3 plus 5. And this is going to be equal to negative 475 over 27. I'm going to erase the question mark that I drew in my ordered pair, and I'm going to write down the fraction negative 475 over 27. And I'm going to go ahead and close the parenthesis on that ordered pair. I'm going to box in my entire conclusion. Two, second derivative test for relative extrema. Second derivative test. Let f be a function such that f prime of c is equal to 0 and the second derivative of f exists in an open interval containing c. 1. If f double prime of c is less than 0, then f has a relative maximum at x equal to c. 2. If f double prime of c is greater than 0, then f has a relative minimum at x equal to c. 3. If f double prime of c is equal to 0, then the f is inconclusive. Next to number 1, I'm going to draw a function that looks like a parabola that opens down. I'm going to draw a point at the very top where the vertex should be at, and I'm going to draw an arrow pointing at that point, and I'm going to write down max next to it. Next to number 2, I'm going to draw a function that looks like a parabola that opens upward. I'm going to draw a point at the very bottom where the vertex should be at. I'm going to draw an arrow pointing at that point, and I'm going to write down min next to that point. 3. If f double prime of c equals 0, then the test is inconclusive. Example 2. Find all relative extrema for f of x equals x raised to the third power minus 5x squared plus 7x. Solution 1. First derivative test. So first thing we're going to do is find the first derivative, and we're going to set it equal to 0, and we're going to solve. So I'm going to write down here that we're looking for f prime of x equals 0. F prime of x is equal to 3x squared minus 10x plus 7. I'm going to set this equal to 0. In order to solve this quadratic equation, I'm going to factor this polynomial. I'm going to use the factoring by grouping method. So I need two numbers that multiply to give me positive 21 and add up to give negative 10. Those two numbers are going to be negative 3 and negative 7. I'm going to rewrite that middle term, that minus 10x, using those two numbers there. So I'm going to write down now the polynomial 3x squared minus 3x plus negative 7x plus 7. Now I can do factoring by grouping. I'm going to group the first two terms, the 3x squared and the minus 3x. I'm going to group the last two terms, the negative 7x and the plus 7. So I can factor out a 3x from the first two terms. That'll leave me with 3x times the quantity x minus 1. I can factor out a negative 7 from the last two terms, so that'll give me minus 7 times the quantity x minus 1 equals 0. Then I can factor out that factor of x minus 1, and that's going to leave me with x minus 1 times the quantity 3x minus 7, and this is going to be equal to 0. I'm going to set each one of these factors equal to 0, so I'm going to have x minus 1 equals 0, and I'm going to have 3x minus 7 equals 0. The solution for the first equation is going to be x equal to 1, and the solution for the second equation is going to be x equal to 7/3. I'm going to draw a vertical line segment so I can separate the work that I did here from the left from what I'm going to do on the right. On the right hand side, I'm going to draw a one-dimensional number line, And I'm going to go ahead and label my critical values of 1 and 7/3. 7/3 also means the same thing as 2 and 1/3. I'm going to go ahead and choose my test points 0, 2, and 3. And I'm going to go ahead and label this number line with f prime, or the first derivative of f, so that I know that this number line is associated with the first derivative test. Now I'm going to go ahead and substitute my test points into my first derivative. So f prime of 0 is equal to 3 times 0 squared minus 10 times 0 plus 7, which is equal to 7. F prime of 2 is equal to 3 times 2 squared minus 10 times 2 plus 7, which is equal to -1, but I'm going to show the work here. This is going to be equal to 3 times 4 minus 20 plus 7. This is equal to 12 minus 20 plus 7. This is equal to -8 plus 7, which is equal to -1. So I'm going to go ahead and label the interval, the open interval from -infinity to 1. I'm going to put a plus sign in that interval, or a positive sign, and I'm going to write down INC, which represents increasing. In the open interval from 1 to 7/3, I'm going to draw a negative sign and circle that, and I'm going to write down the letters DEC, which stands for decreasing, means my function is decreasing in this interval. Now I'm going to choose that test point 3 and substitute it into f prime. So f prime of 3 is equal to 3 times 3 squared minus 10 times 3 plus 7. This is equal to 3 times 9 minus 30 plus 7. And this is equal to 27 minus 30 plus 7, which is equal to 4. Because the 4 is positive, I'm going to draw a little positive sign in that open interval from 7/3 to infinity. And I'm going to also write down INC to represent that the function is increasing in this interval. I'm going to erase the work that I did here underneath the f prime of 3. I'm going to draw a vertical line segment separating the work that I just did here for the number line test. To the right of the vertical line segment, I'm going to write down my conclusion. F has a relative maximum at x equal to 1. In order to find that exact point, that ordered pair, I'm going to have to substitute 1 into my original function. So f of 1 is equal to 1 cubed minus 5 times 1 squared plus 7 times 1, which is 1 minus 5 plus 7, which is equal to 3. So my ordered pair for this relative maximum is going to be at 1, 3. I'm going to draw a horizontal line segment to separate my conclusion of my relative max from my relative min. I'm going to write down f has a relative minimum at x equal to 7/3. And the location of that relative minimum is going to be at 7/3, comma, I don't know the y value, so I'm going to erase the work that I did down below the f of 1. And I'm going to write down f of 7/3. And I'm going to plug 7/3 into the original function. F of 7/3 is equal to 7/3 cubed minus 5 times 7/3 squared plus 7 times 7/3. I'm just going to go ahead and put this into the graphing calculator and come up with my value. So f of 7/3 is going to be equal to 49 over 27. So we're going to write down our ordered pair, 7/3, comma, 49 over 27. And I'm going to go ahead and box in my conclusions. This would be how we find the relative extrema using the first derivative test. Now let's do the same type of problem, but this time instead of using the first derivative test, I'm going to find the relative extrema using the second derivative test. So this is going to be solution 2, second derivative test. Let me rewrite my original function, f of x equals x cubed minus 5x squared plus 7x. The second derivative here is going to be f double prime of x is equal to 6x minus 10. The first step of the second derivative test would be to find the critical values, which I already did here for the solution 1 for our first step. So I'm just going to refer to the top problem where I have x equal to 1 and x equal to 7/3. I'm going to substitute these critical values into the second derivative. So f double prime of 1 is going to be equal to 6 times 1 minus 10, which is equal to 6 minus 10, which is equal to -4. F double prime of 1 is less than 0. That means it's negative. So that means it's going to be concave down. And at x equal to 1, this is going to represent a maximum value. So I'm going to go ahead and draw a vertical line segment here. And on the right-hand side of the vertical line segment, now I'm going to find f double prime of 7/3. F double prime of 7/3 is going to be equal to 6 over 1 times 7 over 3 minus 10. f double prime of 7/3 is going to be equal to 42/3 minus 10. I can reduce that 42/3. So let's go ahead and reduce it to 14. So it'll be 14 minus 10. This is equal to 4. And it's a positive value. So f double prime of 7/3 is greater than 0. That means it's positive. That means it's going to be concave up. This critical value is going to represent a relative min, a relative minimum. F has a relative maximum at x equal to 1, and this ordered pair is going to be at 1, 3. And f has a relative minimum at x equal to 7/3, and this ordered pair is going to be located at 7/3, 49/27. I'm going to go ahead and box in that conclusion. And that's going to be our answer.